Okay, so last set of notes we have to take, again, is chi-square. This time we are looking at what is called a two-way table. A two-way table just has two different variables. That's all that it means. So two-way table just means two different variables. So for example, we might be comparing the class that someone is in with their favorite color. So I teach stats 7th block and 8th block, and so we might be looking at how many people is their favorite color red versus blue versus yellow, so on and so forth. A few things that I did not tell us last time that I want to tell us now. First thing that's really important is chi-square is only for categorical data. So you will never do a chi-square test of any kind for numeric data. It's only categorical. So in this case, that's why I did class versus color, both categorical. The other thing that I want to tell you is that chi-square, there are no confidence intervals. So this unit, you will only do hypothesis tests. Chi-square does not have confidence intervals. Okay, so like I said, we are only looking at two-way tables today, which means we're going to have two different variables, but we are doing two different hypothesis tests. And the test that you choose is going to depend on how the data was collected. So the data that we're looking at right here, class period versus favorite color, the test that we do would depend on how I collected that data. We'll get to this, but did I collect from 7th block and 8th block separately, or did I collect from an entire group of stats students and I asked what period are you in and what's your favorite color? So the first test that we are going to take a look at is called a chi-square test for either homogeneity or homogeneity. You're going to hear it pronounced either way. This test compares the distribution for one categorical variable with multiple categories in multiple populations. Here's what I mean by that. AKA, what I'm saying is that we have multiple samples taken. So that the data above in that table, that would be a test for homogeneity if I took a sample from block 7 and a sample from block 8 separately. I took separate samples, hence chi-square test for homogeneity or homogeneity. How is this different from P1 minus P2? P1 minus P2 is exactly two categories and exactly two groups. So exactly two populations, and in those populations, there's only two options. So a chi-square test for homogeneity, it just is more general. Okay, so what we're going to be doing in a chi-square test for homogeneity is we're going to be comparing two different populations. For our null, we are going to assume that those populations are the same. So if we were looking at our favorite color, we would assume the favorite colors in block 7 have the same proportions as the favorite colors in block 8. So how we write that, for our null, we will say there is no difference in the true distribution, ... and give context. So the alternative then, there is a difference. How do we know if there's evidence for HA? The same way that we did before. What we observed is not the same as what we expected. Okay, so let's talk about how do we calculate the expected values. The expected values, it's going to be a fraction. The numerator of the fraction, you are taking the column total, and you are multiplying by the row total, and you are dividing by the grand total. What I need us to know is this is not on the formula sheet. So the vast majority of the formulas you need are on the formula sheet. This one is not, though. Okay, the conditions, same as they were for goodness of fit. So 10% rule. Large, so all of those expected values have to be greater than 5. And then random. Again, though, that random is either going to be a random sample or a randomized experiment. So treatments. Okay, the formula is still the same. It's still chi-square. So you're still going to be summing up observed, subtract expected squared divided by expected. Degrees of freedom are a little bit different. What you're going to do is you are going to take the number of rows and subtract 1, and then the number of columns and subtract 1. In terms of the p-value, because this is chi-square, it is always an upper-tailed test. So then if you remember, we did chi-square CDF on our calculator. Okay, can you use your calculator? Yes, we're going to do a lot on the calculator. So I'm going to need us to really be with us, with me. Okay, so what I want to do at this point is we're going to do a full example, then we will take a break, and then we will come back to do the other kind. Sound good? Okay, questions on the pieces before we put them all together in a full example. Okay, so here's our example. Inspired by the background music example, a student randomly assigned 20 volunteers to get a red survey, and 20 volunteers to get a blue survey, and 20 volunteers to get a control survey. The first 3 questions on each survey were the same, but the 4th and 5th questions were different. For example, the 4th question on the red survey was, when you think of the color red, what do you think about? On the blue survey, the question replaced red with blue. On the control survey, the questions were not about color. As a reward, the student let each volunteer choose a chocolate candy in a red wrapper or a chocolate candy in a blue wrapper. Do the data provide convincing evidence at the 0.05 level that planting thoughts about color affects color choice? Okay, before we do our test, we need to talk about how do we know what type of test it is. Because when you get to To AP review in all of April, you're going to have to be able to put all of these together. So when you see this data, the first thing that you should be thinking about is, okay, I have two different variables. I have the candy color and I have the survey color. Then we should be thinking, we have two categorical variables. So if it's categorical, you have two options. We could be looking at proportion or we could be looking at chi-square. Because we have those two different variables in the table in which it's given, that is the chi-square test for homogeneity. Our other one is called a chi-square test for independence. So that's what we're going to learn next. So two-way table is either going to be a chi-square test for homogeneity or a chi-square test for independence. The way you determine between the two is how the data was collected. So in this case, we have red survey compared to blue compared to control. So we have three separate samples or treatments. That's why it's a test for homogeneity. Three separate groups. Okay, so now that we know what kind of test it is, let's put all of this down formally. This is a chi-square test for homogeneity. It is upper-tailed because it's chi-squared. Alpha is 0.05. And then normally we say using T or Z. You don't have to say that because we're using chi-square. We've already said it. But chi-square does have degrees of freedom. So we either need to do that here or in the calculation step. For our degrees of freedom, there are two rows, so I subtract 1. You don't count the total. There are 3 columns, I subtract 1. So that gives me 2 degrees of freedom. You do not need to show that work. I'm showing the work so that when you look back at your notes, you know where that 2 came from, but you don't need to show that. So now we're going to do the null and the alternative. You're going to like this, I think. The benefit to a chi-square test for homogeneity or independence, there's no parameters. You don't have to define a p or a mu or anything like that. It's just in words. So our null, there is no difference in the distributions, that's plural, of candy color choice for those who get red, blue, or control surveys. Notice that I used plural, not plural, I used present tense with get. Not those who got, but those who get these surveys. So then our alternative, there is a difference. There is a difference in the distributions of candy color choice for people who get red, blue, or control surveys. Now we're ready to check First one is random. I need us to be clear on this one. We did not survey. We did not take a sample. There were 20 volunteers, 20 volunteers, 20 volunteers. So they were volunteers. We're not checking for a random sample. Instead, in this case, random is treatments. So yes, treatments were randomized. Bless you. Okay, next we need to know, do we have a large sample? Are all of our expected counts greater than 5? So we have to calculate those. If I were you, I would draw a table similar to the table that you have above, so it's very clear which expected counts are which. So this is the red candy, the blue candy, the red survey, the blue survey, the control survey. And we don't need totals. Okay, you need to show work for one of the boxes. I don't care which one. So I'm going to show for this box, the red. Okay, to find that number, I'm going to go back to the table. You take the row total, so that's 26. You take the column total, which is 20, and you divide by the grand total, which is 60. So you take the row total, you multiply by the column total, and you divide by the grand total. So we're going to take 26, we multiply by 20, and we divide by 60. So that gives us 8.67. And then you would keep going. Are you okay if I just tell you what the rest of them are? Great. This is also 8.67, 8.67, and then 11.33, 11.33, and 11.33. And I do want to see that, yes, these are greater than 5. Lastly, 10% rule. In this case, that is unnecessary because there's no sampling. And again, there's no sampling because we have volunteers. Questions? Okay. Calculate step next. So of course, I want the formula. So we have observed, subtract expected squared divided by expected. Like we did before, we want the substitution. I want the first and the last. So when I say first and the last, here's my first one, 13 compared to 8.67. And my other one is 12 compared to 11.33. So if I write that out, I have 13 subtract 8.67 squared divided by 8.67 plus ... And then the last one is 12 subtract 11.33 squared over 11.33. And then from there, we're going to get our chi-square from the calculator, and we will get our p-value from the calculator. Okay, you ready? Let's talk about the calculator. What I want everybody to do, and everybody's going to do this the exact same way. Right now, hit Stat, go to Tests, and then if you scroll down for a while, you should see chi-square test. And what I want us to do is look at what information the calculator needs. So do you see that when you went to chi-square test, it says observed and expected? You guys with me? And mine, I would bet yours says the same, looks like this. Does yours? Observed, expected? And then it gives you the options of calculator draw. So obviously we're going to have to put the observed and the expected in. What is this notation for? I heard it in the back. These are matrices. So the calculator needs the observed values in a matrix. It needs the expected values in a matrix. So what I need us to do right now is quit out. So go second quit. And now you're going to have to go to your matrices. So you'll hit second matrix. Second matrix. Everybody follow so far? Go over to edit. And we're just going to edit matrix A. Matrix A is the observed values. So looking at our observed values above, we need to put these 6 numbers in. We will need to start, though, by changing the dimensions of the matrix. So those 6 numbers that I just highlighted above, what are the dimensions of that matrix? Well, it's either 2 by 3 or 3 by 2, right? It always goes rows and then columns. So there are 2 rows and 3 columns. So once you change it to 2 to 3, you should notice you have 6 numbers in that orientation. Do you? Okay, so go add those numbers in. So you'll do 13, 5, 8, 7, 15, 12. And then quit out. Everybody have the observed matrix in. Everybody follows me. Okay. I think you guys know, bless you, that I like to be efficient, and I do not want us to do extra work. So what I'm going to say is, let's just be lazy for a minute, and we're not even going to bother to put matrix B in. Okay? We're just going to leave matrix A with our observed values. We're going to forget about matrix B. So what I want you to do now is do that chi-square test. So go to stat, go over to tests, do your chi-square test. So observed is in matrix A, expected we're just leaving, and hit calculate. The calculator should tell you that you have a chi-square value of about 6.65 and a p-value of about 0.036. And degrees of freedom 2, which we already knew. You guys agree? So we all got the same thing even though we didn't put the expected values in? You want to see something pretty cool now? I want you to now go look at matrix B. So go hit second matrix and go like you're editing matrix B. And do you see that it has all of the expected values in there? So you don't actually have to calculate them. The calculator will do it for you. So I showed you how to do it. You need to know how to because it could come up on a multiple choice question, but I don't want you to actually do this by hand. You don't have to show any work. So if I were you, when it's a chi-square test for homogeneity, immediately plug the numbers in and just get the expected values from the calculator. Don't calculate them by hand. But you need to know how in case it comes up on multiple choice. And then, of course, you would draw a figure. I'm not going to because I don't have a whole lot of work, or a whole lot of room, rather. So we're just going to write plus figure. Questions before we write our conclusion? Okay, this last question, follow-up analysis, we're not going to do that, so just cross that out. Cross that out. We're going to write both conclusions, and then we will take a break. So 0.036 is less than 0.05, so I'm going to reject. I reject the null. as I have convincing evidence that there is a difference in the distributions of color choice for people receiving red, blue, or control surveys. Let's make sure we answer the question because we didn't directly use the wording for the question. Planting thoughts about color affects choice. So we would say yes. There is evidence that planting thoughts affects color choice. Before we write the p-value, I have two questions. Can we say definitively, or do we have reason to say, that the color of the surveys is what caused the difference in the candy choice? So my question is, can we say that the different color surveys is what caused the change in the color choice for the candies? Yes. When can we show cause and effect? It's an experiment. Is this an experiment? Yes, it is. Who does that conclusion apply to? Augie?
People like the volunteers.
Very good. These volunteers and people like them, not everyone. Okay, let's interpret the p-value real quick and then we will take a break. Assuming no difference in the distributions of candy color choice based on survey color. .036 is the probability of obtaining, and it's going to be worded just like the other one, like goodness if it, of obtaining the observed distribution or more extreme based on chance. Okay, that is the first test, a test for homogeneity. The next test, a test for independence, looks almost exactly the same. The only difference is the way that things are worded in the null and identifying the test. So we're going to skip around a little bit. Not want to do this next page, so skip to the page after it. We are going to take a look at these, and then we will go from there. We're going to answer these questions briefly, and then you're going to do an example that I'm going to start you out with. What does it mean if two variables have an association? So, association, or sometimes saying they are independent or dependent, what that means is knowing the value of one variable gives us more information about a second variable. So for example, we've taken a look at this before. If I'm looking at what is the probability that someone is in AP Stats given that they're a senior? So I take a senior at random. What is the probability that that person is in AP Stats? Probably a pretty low number, right? It might be like 0.2. But then if I say, what is the probability that they're a senior if I know they're in AP Stats? If I know the person's in AP Stats, what's the probability that that person is a senior? That number is a whole lot higher because almost all of you are seniors. Yeah, this was, I didn't do this right. We don't care about that one. Sorry, let's backtrack. What I should have had us look at instead is what is the probability that someone is a senior? So if I choose a student at random, probability that that student is a senior is about 0.25, right? About a quarter of you at this school are seniors. But then if I tell you the person's in AP Stats, the likelihood of being a senior is a lot higher. So we say that being a senior and being in AP Stats, those are dependent. They have an association. When I tell you someone's grade, it changes or gives us more information, vice versa. Okay, when we talk about a test for independence, our null is we assume no relationship. So we are going to assume that there is no relationship between the two variables, and we are going to look for evidence to the contrary. This next question is by far the most important one. How do you know it's a test for independence versus a test for homogeneity? So first thing, both tests start with a two-way table. Our best indicator is how the sample is collected. Here's what I mean. A test for independence is one sample and then two or more variables. Whereas a test for homogeneity, it's going to be two or more samples. But we are only looking at one variable. So that was, we had the people with the blue surveys compared to the red surveys compared to the control surveys. That was homogeneity. Independence, it's an entire sample, and we are collecting multiple pieces of information. In terms of the expected counts, the test statistic, and the degrees of freedom, they're all exactly the same. No differences. And the conditions, also the same. The only difference is that random, it is a single random sample. Test for independence is only one sample, so we just need to be sure that we are writing in a singular tense. Okay. So what we're going to do is we're going to do one example. I'm going to start us out in terms of knowing what kind of test it is and how to write the null and the alternative, and then in your group you will complete the example. That is really the last thing I have for us to do today. That's what I want to get through. Okay, next page. Is your index finger longer than your ring finger? Is relative finger length associated with gender? A random sample of 460 high school students in the U.S. was selected and asked to record if their pointer finger was longer than, shorter than, or the same length as their ring finger on their left hand. The gender of each student was also reported. Do the data provide convincing evidence at the 0.05 level of an association between gender and relative finger length? Okay, when you see this, what should be going through your head is, I have a two-way table that suggests that this might be chi-squared. Then I'm looking at, are my variables categorical? That's a necessity for chi-squared. They are. Okay, so I have categorical variables. I have a two-way table. So then this is either a test for homogeneity or it's a test for independence. So to decide, you are looking at how the data was collected. It says a single sample of 460 students. That is a test for independence. Now, this same data could have been a test for homogeneity if it was a sample of men and a sample of women. So if we took a sample of men, sample of women, then it's a test for homogeneity. But because it's a single sample and we asked what is your gender and take a look at your fingers, that's why it is independence. So I'm going to start us off with shoes and then you all will continue from there. Okay, so this is a chi-square test for independence. It is upper-tailed. Alpha is 0.05. And then for degrees of freedom, we have 3 subtract 1, 2 subtract 1, so 2 degrees of freedom again. Okay, so in terms of our null and our alternative, it says, is there evidence of an association? That just means a relationship. Is there evidence of a relationship? So we are going to assume no. So our null is, there is no association between relative finger length and gender. Our alternative is there is an association between relative finger length and gender. These could be worded differently. So instead of no association, you might see that the variables are independent. So it could be worded, relative finger length and gender are independent. It's the same thing as no association. Instead of association, you could see dependent. I don't care which one you use, you just need to recognize that they're the same. Questions for me? Lucy.
How do we know to assume that there's no association for the null? Does it just depend on the situation?
Great question. We are always going to assume no association. So for independence, always assuming no. Okay, right now, you're going to move together in your groups and finish this question, please. Let's talk about this one. This is my old answer key, so it has the first C's, it's just with different words. So the first assumption, we should have checked that it is a random sample, single sample. That's it. You do need to check the 10% rule because this was a sample, so there needs to be more than 4,600 high school students. All of the expected counts have to be greater than 5. You do not need the formula. You do not need work. All you need is the expected values. It would be lovely if you could put them in a table that's organized in some way, shape, or form. I think as I was walking around, I told all of us, in order to get those values, you have to carry out the test on your calculator. So some of you were putting the observed values in matrix A and then wondering where the expected were. The calculator doesn't do the expected until it carries out the test. For the calculate step, I want the formula, substitution. We should get a chi-square value and a p-value. We should have just copied the figure directly off of our calculator. I have alpha labeled. You don't need that. You just need to copy it, shade. Hopefully we compared the p-value to alpha, so we're failing to reject the null, which means there is not enough evidence of a relationship or an association between finger length and gender. I'm occasionally seeing still people accepting the null, so saying, I fail to reject the null, and I believe there is no association. That's not the case. If you fail to reject the null, it's because we do not have enough evidence for the alternative. And then the p-value, I worded a little bit differently, but you should have said something like, assuming no association between gender and finger length, 0.356 is the probability of the observed distribution, or one more extreme, by chance. How do we feel about this? Are we getting sick of hypothesis tests? But I'm like, besides being tedious, it's just doing the same thing over and over and over again, right? You guys want to hear something exciting? The examples we do on Friday will have confidence intervals and hypothesis tests, but pretty much just the number part and the conclusion. We will not be doing any 4-step processes on Friday. Pretty exciting, right? Questions for me?